Hello and welcome back to Multidimensional Integration, the video series where we explain how to solve integrals in Rn. And in today's part 4, I will show you how Fubini's theorem works in practice. Indeed, in the last video we have discussed the so-called Fubini-Tonelli theorem, and here I show you an example of it. But you already know, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And I should also tell you, as a Steady supporter, you can easily access the additional material on my website. Just click the link in the description to download PDF versions and quizzes. Okay, then let's immediately start the video by recalling the important Fubini's theorem, which is also known as the Fubini-Tonelli theorem. Some authors use the two names to distinguish some details in the two theorems, but I use the names interchangeable here. Or you could say, I simply put both statements in one theorem. And now the setup is not so complicated, we just need a measurable function which satisfies one of two conditions. Either it's a non-negative function or it's an integrable function. So either you know something about the values or you know something about the integral of the absolute value. However, in both cases we want that the function has a domain given by a Cartesian product in Rn plus m. So we have a set A in Rn and a set B in Rm. And then the n plus m dimensional integral of f can be calculated by two integrals, 1 over a and 1 over b. They are put together in such an iterative way. And in particular, we also get that the order of the two integrals here does not matter. Okay, so this is Fubini's theorem as we know it. We can apply it if the function f is defined on a Cartesian product. Therefore, this is the first problem. What do we do if we don't have that? So for example, just imagine that we have a function defined on R2. And then the domain is not given by a rectangle, but maybe by this curved form. So f is defined on U, and this inside part here should be U. So as we see it here, Fubini's theorem is not applicable to this function f. It would only be possible if we could extend the domain to a rectangle. And maybe not so surprisingly, this is exactly the solution of this problem. So we define intervals a and b and extend the function. And of course, this is always possible no matter what the domain U in R2 actually is. And then what we get is a new function, and maybe let's call it f tilde. So there we have the domain as we want it, and if we restrict f tilde to U, we should get out f again. And since we don't want to change the integral of f tilde should be 0 outside of U. This means the definition here is really easy, we just define it piecewisely. We just have f at the point x and y if x and y lie in U, and in the other case we would set it to 0. So a really natural definition which solves our problem in general. Which means that the whole thing does not only work in R2, but also in Rn plus m in general. Simply because the integral of f is the same as the integral of f tilde. And now we see, for this integral we can simply apply Fubini's theorem. And then, in the two integrals we have here, one can definitely use that at some parts in the integral we simply have 0. And this also implies that in applications, one order might be better than the other order. Simply because the calculation with all the zeros involved could be simpler in the one integral than in the other. So this is exactly how we will apply Fubini, and I will show you an example such that we can see this procedure in action. And in order to keep a good visualization, let's stay in R2. This means, in the end, we only have to solve two one-dimensional integrals. Okay, and now in contrast to before, let's make this domain U concrete. Hence here on the y-axis I want to go until the number 3, and here on the x-axis we are satisfied with 1. This means the whole picture here is stretched in the x direction. And now what comes in here is a graph of a function which is part of a parabola. More precisely, the function should be given as 3 minus x squared. And now we have all the boundaries. This set in R2 is our set U. It does not look so complicated, but it's not quite a Cartesian product. Okay, and now what we could do is to put a third dimension to this picture. This means we have the xy plane here on the bottom and the set U inside. And then in the z direction we would find the values of the function f. So we could say here on the left hand side we find the domain picture, and on the right hand side a graph picture. And there the graph of f would lie as a surface on top of this domain. And now I want to take a really simple graph surface, namely it should be a constant function. And in fact, the nicest case would be that this constant is given as 1. And now you already know by the visualization of an integral that this volume here between the xy plane and the graph of the function is exactly our integral. More precisely, it's the integral of f over the set U. And you know a common notation for a two-dimensional integral is simply dxy. And now since we have the constant function involved, we can just write 1 instead of f. Okay, so to make it clear again, this integral here describes the volume on the right hand side. However, since the only thing that happens in the z direction is a height of 1, we can also say that this integral describes the area of U. In other words, you can use a two-dimensional integral to calculate a volume in R3 or an area in R2. Okay, so this is our interpretation, and now I can show you how we can use Fubini to calculate this integral. And as explained before, first we have to bring U into a Cartesian product. This is not hard at all, we just increase U to a rectangle. However, there the function we integrate changes because it's only 1 at U, and outside of U it should be 0. And this is already the whole idea, because the description of this function f tilde already tells us how to solve the integral. So here we can say f tilde is equal to 1 if x lies in the interval 0 to 1, but then y depends on the chosen x. Namely, y lies between 1 and the value 3 minus x squared. So in other words, the boundary of this domain U is now put into the definition of f tilde. And to finish the definition, it's 0 for all other cases. Okay, so everything is fine here, and now we can just use Fubini's theorem. Which means now we can write this two-dimensional integral as two one-dimensional integrals. And it already makes sense to write the integration with respect to x to the outside integral. Simply because we already have a nice description how y depends on x. In fact, we can immediately look at the one-dimensional integral in the middle, where we see that the function we integrate is 0 whenever y does not lie in this interval here. Therefore, we can nicely simplify this. We can write 1 instead of f tilde and 3 minus x squared for the upper boundary here. So we see this is a really easy integral to solve. Indeed, it's just the upper limit minus the lower limit, which is 1. Hence what remains is just one one-dimensional integral which we have to solve. So this is how Fubini works. Step by step we go down until we only have to solve one-dimensional integrals, and we know how to do that. So here I don't have to show you the last calculation, and what we get out is 5/3. Hence, now you know if someone asks you about the area of this domain U, this is what you have to do, and this is the result. And obviously, if you know what you do, you can skip the step of writing down f tilde. For us here, it was just the explanation that Fubini also works in more complicated cases for the domain. Okay, so from now on, you have Fubini's theorem as a tool to solve integrals. And I can already tell you, we will talk about more tools with the next videos. So I really hope we meet there again and have a nice day. Bye bye.